A very good morning, good afternoon and good evening to all the participants and the candidates for this course, which is titled Application of Forecasting, Regression and Time Series Models under MOOC-NPTEL. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. Now, as you know, this course covers three main topics, which is the forecasting techniques. Next one is basically the regression models, and third is basically the time series. So, we are in the first topic, which is basically the concepts of forecasting model, which is the averaging techniques to be used in forecasting and different ways of trying to predict. This is the first lecture for week 2, hence is lecture number 6, and the coverage would be AIC. What is AIC? I will come to the details. Ideas of overfitting and underfitting and what is the problem. We will consider different metric such as mean error, mean absolute error, mean squared error, mean percentage error, mean absolute percentage error and U statistics. Having said that, we will try to cover, but any coverage which is left after the 6th lecture, it will basically continue in the 7th one. And as I have told you already, that the slides would be updated accordingly based on the coverage which we do for each and every half an hour for the lecture. Now, what is AIC? So, for forecasting, we use the value of AIC, which is known as Akaike's information criteria, and it gives you, this is basically a collection of models or different type of metric, which estimates the quality of each model. And what I mean of the quality of each model is basically how good or bad the prediction or the forecasting is. Now, when I use the word of how good or bad the forecasting technique is, it basically means that what is the metric based on which the forecasting concept is being analyzed, number 1. And number 2 is that how would you be able to predict to the maximum possible extent, trying to basically minimize the so called error for future forecasting. When I use the word error in many of the discussions as we proceed, I will be using another word like loss, or say for example, the word of variance. They would be used interchangeably, but that does not mean the overall concept is different, but the idea is that how you are trying to basically express the efficacy of the model which you are trying to utilize for the prediction and the forecasting concepts. So, as I was reading, so AIC gives a collection of models for the data. It estimates the quality of each model relative to each other. So, obviously, you will try to compare the models against each other, not on a standalone basis, and provides a means for the model selection based on which you will make the final decision. Now, one thing should be made very clear, that there is no ultimate model, in the sense one model may not be applicable for all the problems, it may not be possible. So, you have to use, depending on what criteria you are going to use, what metric you are going to use, you have to select the model accordingly. So, say for example, you will see later the exponential moving average may be applicable for one case, while the Halt-Winter method may be applicable for other different type of case, depending on the data. So, if you try to utilize the exponential moving average for the second case and try to use the Halt-Winter for the first case, you may not get the best result. So, it is not that the exponential moving average or the Halt-Winter method is bad or is not very efficient. It basically means that in which context you are going to utilize it. AIC is used extensively in information theory and statistics, even though we would not be applying that to that extent in our case, but we will basically try to compare the models as I have discussed. So, the concept of AIC is given. So, these ideas which I am stating are thus being stated for the information, that means how you will utilize, but the actual application would be with respect to the different models when you are trying to utilize with respect to different metric. So, when I use the concept of AIC basically means it is the logarithmic of a function where mk is the model with the dimension given as k. Now, what I mean by dimension would basically depend on what are the different type of x values you have, how many x values you have. When I am considering x as the main data based on which we are trying to do the forecasting. So, in case say for example, for the regression model we are utilizing and there is one dependent variable and 3 independent variables, and obviously the dimension will be calculated accordingly depending on 3 different independent variables, 1 dependent variable, and how many different type of readings are there, it will be considered. AIC model estimates the relative amount of information lost by a given model. If the case is that any model is not able to give the prediction, the forecasting to 100% efficiency, there would be a loss. And the AIC model basically tries to give the idea to in which model the loss is minimum, because amount of loss being minimum, it basically gives us the idea that amount of data which is not being utilized for the forecasting model is the least. Because if you are trying to utilize the data, trying to basically minimize, considering there would be white noise, we are trying to basically minimize the effect of the white noise, obviously the forecasting would be the best. So, here the idea is basically try to choose that model where the white noise or the loss of information is, the white noise is least, loss of information is also the least. In estimating the amount of information lost by a model, AIC deals with the trade-off between the goodness of fit of the model and the simplicity of the model. So, what is the idea of goodness of fit or precision of estimation? These two important words will basically come later on when we discuss the ideas of regression model under different context. And what is the context would basically be made very clear as we discuss the multiple linear regression models. In other words, AIC deals with both the concept of risk of overfitting and underfitting. Maybe if underfitting means that if the model is not fitted well, then obviously there is a huge amount of loss, and the idea would be that the prediction is not good. Overfitting means that you are trying to basically assume the amount of theoretical assumption would be such that you will get a good result, but in practical sense it may not be applicable at all. That theoretically your results are fine, but in practical sense they may not be applicable at all. So, you have to basically make a compromise accordingly. Now, let us basically consider the different metrics which are utilized in order to analyze a model and try to find out that what is the efficiency of the model depending on different metric. Now, before we do that, we will basically clarify 3 important points. Number 1 is this, that whenever we consider, we will denote as YT as the actual value. Y is the symbol for the actual value, and the suffix t would basically give you at which time period, because all these data which you are trying to utilize are dependent on the time frame, because on the x axis, as I have mentioned, you will measure the time, and along the y axis you will basically measure the actual value which we denote by y. Here ft, I am using a different color, would basically be the forecasted value. So, obviously for each y, depending on the past data, we will try to forecast. So, that forecasted value will be given by f, and again I am repeating, y is the actual value. And obviously, if the values do not match, there would be a difference. That difference would basically be denoted by E, which is the error. I will again mark it with a different color, consider blue. So, E would basically be the error based on the difference between yt minus ft. Now, whenever I am using the t, remember that is for the same time period. So, if t is the next time period, it will be t plus 1. If t is basically the previous time period, one period before in the past, it will be denoted by t minus 1. Similarly, if it is 2 time periods in the past, it will be denoted by t minus 2. And if you go into the future, if it is t plus 1, t plus 2, obviously it will denote that as you move one period at a time corresponding to the idea which is being expressed. Now, what are the different metric based on y, f and e, and obviously the suffix would be applicable. The mean error is given by this, that means you want to find out the average of the errors. So, if y, I will denote if y1, and if f1 are given, I am using different colors for, so there is no confusion. So, the y value is, say for example 12, next time period is 14, next time period is 17. The f value is given by 13, is given by 15, is given by 14. So, the corresponding value of E, which is error, I will utilize a different color. It should be T, this should be T, and this should be T. So, the values of the errors would be given as 12 minus 13 is equal to minus 1. Next one will be correspondingly 14 minus 15 is minus 1. Third one is 17 minus 14 is plus 3. So, when I consider the mean error basically means the sum of all the errors divided by the number of reading. So, the means absolute means error here I will denote as minus 1 plus 3 by 3. So, it will be basically plus 1 by 3. This would basically be the idea of mean error. When I go to the concept of mean absolute error, you see basically the average of all the errors with the absolute sign. So, here it will be mean absolute error. I am using the same color because violet is being used to find out the mean absolute error. Okay, let me make a different color, so this confusion would be minimized. So, it will be 1 by 3 because number of reading, and the error which you have is minus 1 basically means 1 plus again minus 1 plus 3 is 3. So, it basically means 5 by 3. So, that is the mean absolute error. If I consider the mean squared error, so again I will use a different color, consider I am using dark red, the number of reading is 1 by 3 and the error squares are 1 square is 1, then again error square is 1 square is 1, 3 square is 9. So, the value becomes 11 by 3. So, this is the mean squared error. Now, consider the concept is further extended. Again, without repeating it, y t is the actual value for time period t, f t is basically the forecasted value at time period t, E t is basically the error at time period t, and error is basically the difference between the actual value and the forecasted value. Now, I have the mean percentage error. Mean percentage error is basically given, if you see the formula, the difference between y and f divided by this actual value which y. So, if I have, say for example, the data which I have utilized, I will use the blue for y and the values were, if I just go back to the last slide, it is 12, 14, 17, 13, 15, 14, 12, just 1 minute if I missed 12, 14, 17, then I have the forecasted value, it is 13, 15 and 14, and if I have the error E t, it was given by, the error value was basically -1 plus 3. Now, when I go to the mean percentage error, so mean percentage error would be the difference divided by y. So, I will consider color green. So, for the first value mean, so this will be percentage error. So, I will first find out the percentage error P. So, this will be given by the difference -1 by 12, because 12 was the actual value of y t. This star is basically the multiplication multiplied by 100. The next value would be again minus 1 divided by 14, 14 was the actual value, multiplied by 100, and the last case would basically be plus 3 divided by 17 multiplied by 100. So, this is the percentage error, and the mean absolute percentage error would be, you add up all these values, add them up and divide by 1 by n, where 1 by n is basically 1 by 3, because that is the number of readings which you have. So, that will give you the mean percentage error. Only remember that you are taking that error divided by the actual value. Now, when I come to the concept of mean absolute percentage error, so it is the word absolute is there. So, in that case the idea is exactly the same, only rather than the error with the sign we will just take the absolute error. So, in that case if I consider, I will erase this. So, I erase this part which is related to, I will use the black color. So, this is absolute percentage error. So, this is 1 divided by 12, 1 is the error with the sign being positive, 12 is basically the y 1 value. So, the 1 by 12 into 100. Similarly, for the next value, it will be 1 divided by 14 multiplied by 100, and the last case is 3 divided by 17 multiplied by 100. So, when I take the mean absolute percentage error, I add up all of them, and this 1 by n is basically is equal to 1 by 3, because there are 3 is the number of readings which you have. Remember, in the denominator, I am repeating time and again, in the denominator is the actual value y with the corresponding suffix. Now, what further discussions about this different type of metric? This mean error will only tell you if there is a systematic under overestimation called the forecast bias, and it does not give much indication as to the size of the typical error, because when you add up the errors with their sign, it may be possible for very large positive and negative errors, the total sum may actually turn out to be 0. In the case, say for example, in 3 instances, the errors are minus 20, minus 30, minus 40, and in other 3 instances the same data set, the errors are plus 20, plus 30, plus 40. So, when you add up the errors, they would basically cancel and make it 0. So, the quantum of deviation is not the information which you will get. Mean absolute error has that advantage of being more interpretable and is easier to explain to non-specialists, because that idea of negative error, positive error being there is reflected in the case that you are basically considering them with the positive sign. So, that hence minus 20, minus 30, minus 40, which were negative, now becomes 20, 30, 40. So, when you find out the mean absolute error, they would add up, in the sense the values of 20 will be multiplied by 2, values of 30 will be multiplied by 2, values of 40 will be multiplied by 2. Hence, the quantum of the error would be there such that it is easy for you to explain to any layman. Mean squared error has the advantage of being easier to handle mathematically, and the reason being, mean square error when you are taking, and when you try to minimize the mean square error, it is akin or exactly equal to the concept of trying to minimize the variance. Variance is basically the second moment. So, trying to basically minimize the variance basically gives you the idea that you are trying to minimize the dispersion, and that is what the main idea of any forecasting concept should be. That means, you are trying to minimize the variability, the dispersion, the positive and negative fluctuation. But there is a problem, even though the problem may not be to that extent, but the problem still remains. So, in mean squared error, what you have is basically you are squaring the error. So, if there is an error of minus 20, it gets squared and it becomes 20. If there is an error of minus 100, it basically becomes minus 100 into minus 100. That means, is basically it squares and it explodes. So, any outliers which are there definitely do have some significant set of information which is given into the calculation of MSC, and then obviously if somebody tries to analyze the MSC results without having a look into details about the outliers, then it may not be able to give the right answer. So, you may think that the errors are very high, but the actual concept may be because there are outliers which needs to be removed, and that may not be considered if somebody is not careful in trying to understand the concept of MSC, utilizing the practical ideas how the data has been collected. The mean absolute percentage error is only meaningful if the scale has a meaningful origin. Example should be avoided when using temperature scale of Fahrenheit, Kelvin and centigrade, because these Fahrenheit and the centigrade, while K has a different origin, so it basically has an absolute value of 0. So, try to utilize the concept of MAPE, mean absolute percentage error, for the cases when the concept of the origin of the scale or the 0 value of the scale or some datum based on which the scale is being utilized or the measurement is being done is absolutely known without any ambiguity. An MSC or MAPE of 0 can always be obtained in the fittings phase by using a polynomial or sufficiently high order curve. But the idea is that we want to be very scrupulous, we want to be very theoretically perfect in trying to get the result, but in trying to analyze perfection in the theoretical results, if the practicality of the model is being ignored, it does not make sense. So, if you remember, I have mentioned in this class few minutes back that the idea of AIC is basically there may be problem of overfitting, there may be problem of underfitting. Underfitting we understand, but the idea of overfitting may be a problem in the sense that you are trying to be very theoretically perfect, where the assumptions are theoretically fantastic, but in the practical sense if they do not work, it does not make any sense in trying to utilize such a model, and this is the idea which is being mentioned here. Different methods use different procedures in the fitting phase, and we will see that as we proceed, that using the mean squared error, mean absolute error, MAPE and all these ideas which are there. The relative measures all give equal weights to all errors in contrast to the mean squared error, which squares the errors and thereby emphasizes large errors. This is exactly the idea which I mentioned, that when you are squaring the errors, an error of minus 100 would basically be multiplied by minus 100. So, it becomes minus 100 into minus 100. So, obviously, it explodes. That is not the problem, so called problem in the other cases like the mean error or mean absolute error. So, all these problem in of the square of the error may not be here, but obviously, they have their own issues which I have just mentioned. So, again I am repeating, when you are trying to utilize the mean squared error, be careful that any outliers have to be removed, such that trying to deduce the answer from the mean squared error when these outliers have not been removed may be a problem, and you may not be able to get the right answer. So, it will be helpful to have a measure that considers both the disproportionate cost of large errors and provides a relative basis for comparison with naive model. Naive model means which are the layman's model, which are based on very simple assumptions. And one measure which basically understands that and takes this consideration of trying to consider and the disproportionate cost of high errors and then try to eliminate that to the maximum possible extent is the idea of the U statistics. So, I will give you the formula for the U statistics, and we will, when we utilize that, we will come to that later on. Consider we have a data of n observations starting from y1 to yn, and obviously we will denote by yt, and as we know ft and et would be the corresponding forecasted value and the error term. Here we consider yt as the actual value, ft as the forecasted value, and we also would consider E t as the error. So, Again I am repeating yt as the actual value, just 1 minute, ft as the forecasted value, and u statistics is being utilized, for which I will use the color violet. So, u is the u statistics, and what it is? Pay attention to the numerator and the denominator for the u statistics. If I consider the u statistics, the numerator basically has the actual relative change values, which is known as FPE t plus 1. What is t plus 1 here signifies is basically I am taking the ratio of y t plus 1, which is the actual value for 1 day after, minus yt, which is basically the actual value of today, divided by yt basically gives you the percent or the decimal change in this forecasted value with itself. It has nothing to do with the error or the forecasted value. We are taking the actual value. My apologies, you are taking the actual values. So, you are trying to find out the change in decimal terms about the actual value, which is yt today. Next day it is yt plus 1, and based on that we are trying to find out the ratio. While if I go to the forecasted relative change, which I will highlight using the dark blue color, it gives you the ratio of, in the numerator you have the difference between the forecasted value for 1 day later minus the actual value of today, divided basically by the actual value of today. So, if I compare these two values, in both the cases the denominator are same. In the numerator, in one case you have the difference between the actual value of today and the actual value of 1 day later, considering 1 day is the difference. And in the second case, when you have the forecast relative change, you are trying to find out in the numerator the difference between the predicted or the forecasted value of 1 day later minus the actual value of today. So, if you use that, the concept of in the u statistics, basically you have this, you have the square of these, you are not taking the sum of them. The reason being that if you take the sum, it may be possible the numerator value may be 0 or the denominator value may be 0. Numerator value means for the u statistics. So, hence you square them, find it out for all the values starting from t is equal to 1 to n, and square root of that will give you the u statistics. I will come to the application of the u statistics utilizing the data. So, with this I will end the 6th class, which is basically the first class in the second week, and continue discussion about u statistics and its uses later on. Thank you very much and have a nice day.